Welcome to the Global WarWatch Network. Before we jump in, if you enjoy getting straight to the point on complex tech and defense topics, do us a favor and hit that subscribe button. All right, today we are looking at the incredible science behind one of the most intense moments in aviation, ejecting from a fighter jet. We're going to explore how engineers are making that life-or-death moment safer, not just for the pilot, but for the environment too.
So let me just throw this question at you. The Canopy on a modern jet fighter, it's an absolute beast of engineering, designed to take a bird strike at supersonic speeds without flinching. It is unbelievably strong. So, when everything goes wrong and you have to get out, how in the world do you get through that? The answer isn't about using more force. It's about being much, much smarter.
And that brings us to our first section. We're going to look at the amazing technology that's built for just one thing, making a split-second escape possible.
So here's the paradox, right? The very thing that's there to keep the pilot safe, this incredibly tough, thick canopy, is also the biggest thing trapping them inside during an emergency. You can't just punch your way through it. You have to get rid of it, or at least a piece of it, pretty much instantly.
The solution they came up with is just brilliant. It's called a Miniature Detonating Cord, or MDC. It's basically a thin little line of explosive that's glued to the inside of the canopy. Now, the really cool part is how it works. It's not the explosion itself that breaks the canopy. It's the thin metal tube, the sheath around the explosive, that shatters into tiny, super-fast fragments. Those are what actually cut through the canopy.
Let's walk through it. First, the pilot pulls the ejection handle. That kicks the whole thing off. Then, an explosion rips down that cord at over 7,000 meters per second. No, that's not a typo. It is ridiculously fast. That detonation instantly shatters the metal sheath, turning it into a focused cutting tool. And finally, those tiny metal pieces slam into the canopy, fracturing it perfectly along that line. The pilot's seat then fires right through the opening. The whole thing is over in the blink of an eye.
So this life-saving tech has been working great for decades, but it has a hidden, pretty serious problem. And that brings us to our next section, the lead problem.
For the longest time, the metal they used for that critical sheath was lead. And look, from a pure engineering standpoint, it made perfect sense. Lead is dense, which gives the fragments the punch they need. It's ductile, meaning you can shape it easily without it breaking. And it's cheap to make. It really was the perfect material for the job.
The problem, as we all know now, is that lead is incredibly toxic. Using it is a major health and environmental risk, from the people who make these things all the way to getting rid of them. So as safety rules have gotten tougher, the aerospace industry got a new mission: find a replacement and find it fast.
And this puts engineers in a really tough spot. On one hand, you have lead alloys. They work perfectly, but they're toxic. On the other hand, you've got lead-free options that are safe, but they have to perform just as well. They need that same density, that same flexibility. Finding one material that ticks all the boxes is a huge, huge challenge for material scientists.
So, how do you solve a problem like that? Well, this is where some fascinating research from Brunel University London comes into play, as they set out to design a better, safer alloy from the ground up.
The researchers decided to focus on alloys that were mostly tin. They tried out a few different recipes, like mixing tin with copper or with zinc and bismuth. And look at their goal here. They needed something that was super ductile, able to stretch more than 70% of its length without snapping, but also at a specific, moderate strength. If it was too strong, it wouldn't shatter right. If it was too weak, it'd just fall apart.
But here's where they got really clever. They figured out that what the alloy was made of was only half the battle. The other half was how they treated it. They used a process called rolling, where they passed the metal through heavy rollers again and again. It's kind of like a blacksmith hammering a sword or even kneading dough. The physical work completely changes the material's internal structure. And this slide shows you exactly what that does. On the left, that's the alloy's internal structure right after it was cast. The grains are kind of big and clunky. But on the right, after 8 rounds of rolling, look at that. The structure is totally transformed. It's now fine, stretched out, and all lined up. That tiny change on a microscopic level makes a massive difference in how the alloy performs in the real world. Now this is the big aha moment. They started with a tin-zinc alloy. Now watch what happens when they add just a little bit of another element, bismuth. With just 1% bismuth, the strength shoots way up. At 5%, it's nearly double. But here's the crazy part. Look at the elongation, its ductility. It doesn't go down, it actually goes up. In materials science, that almost never happens. Usually, when you make something stronger, it gets more brittle. This stuff got stronger and more flexible at the same time. That's a huge win. And here is what it looks like.
This is basically a map of the final successful alloy's internal structure. All those fine, uniform grains you see there are what give this new material its amazing properties. This is the structure that's strong enough, ductile enough, and, most importantly, safe enough to finally replace lead.
So what does all this mean for the future of keeping pilots safe? Let's bring it all together.
This chart really tells the whole story in one clean picture. You can just see that massive leap in strength as they added more bismuth. This wasn't just a tiny improvement, it was a total game changer that allowed them to meet the incredible demands needed for these devices.
So the result of all this hard work, this combination of smart chemistry and clever physical processing, is a brand new generation of lead-free materials. And they aren't just a good enough substitute, they are highly engineered alloys specifically designed to work in one of the most extreme situations imaginable, all while being much safer for us and for the planet.
And that kind of leaves us with one last big question. This amazing research solved one very specific, very critical problem. But it makes you wonder, what other essential technologies that we rely on every day, from our phones to medical equipment, are still using toxic materials, just waiting for the next great engineering breakthrough?
And that's our look at the science of ejection seats. If you found this as interesting as we did, please hit that like button, share it with a friend, and make sure you're subscribed for more. We'd love to hear your thoughts down in the comments section. You can also join us on social media. All the links are right there in the description. Thanks for your time, and we'll see you on the next one.